Hello everyone, this project is part of 5th semester Organic Chemistry Department of Mathabhanga College. In this presentation, I will be discussing about the chemical shift effect in NMR spectroscopy. NMR spectroscopy was first observed by Bloch and Purcell. They received Nobel Prize for it. NMR spectroscopy is the most powerful and versatile analytical technique used by chemists today to determine structure and dynamics of molecules. The weight varies from 1 to 10 kilodalton of the molecules. Mostly organic and biomolecules such as proteins are studied by NMR method. The physical basis of NMR lies at the nuclear spin and the magnetic property of nucleus. Nuclei of the certain isotope possess non-zero magnetic momentum, such as half, 1 or 1.5. Only these isotopes are observable in NMR spectra. Most commonly studied isotopes are proton, that means H1, and carbon-13. Magnetogyric ratio of proton is much higher than the other available isotopes. Also, the natural abundance of proton, that means H1, is the reason that is why the proton NMR is mostly used everywhere. And the magnetogyric ratio is high of proton, that makes it highly sensitive to NMR spectroscopy. From the absorption spectra of NMR, we received a digital data in which a frequency axis is horizontally presented. Proton resonances are distributed along the axis in the various positions. The structure information we get from the spectroscopy are as follows. The position of the signal peak indicates the type of hydrogen that is what is chemical shift is about. Number of the hydrogen, secondly, is the each type of known from the peak intensity and number of peaks. Number 3, splitting in the spectra gives info about the neighboring environment of the various hydrogen atom. This is the chemical splitting effect. Here we can see ethanol NMR spectra. For example, there is 3 different kind of proton have 3 different resonance energy, and the frequency also give rise to 3 separate peaks, identifiable by their ratio of 1:2:3. That means the number of hydrogen in each type. The hydroxyl group and the methylene, that means CH2, and the methyl CH3 group. This is the first observed NMR spectra in 1951. That is why the image is very low quality. Now we'll be talking about the origin of chemical shift effect. When a nucleus is placed in an external magnetic field, the proton acts as a tiny magnet, and an NMR frequency is determined by the gyrometric ratio gamma and the strength of magnetic field B. But the actual force experienced by the nucleus in molecule is slightly less than the B0. The surrounding electron cloud will also generate a magnetic field of their own, which act in opposition to the applied one and influence the resultant field at nucleus field magnetic. The increase in the electron density in nucleus local environment causes decrease in the B effective. By higher electron density and distribution, the absorption frequency is lower for transition, which is called shielding. The proton is said to be more shielded. Hence, the less surrounding electron is caused by de-shielding effect. Usually, CdCl3 or TMS, tetramethylsilane, is used as a standard solver. It is most suitable compound for both proton and carbon spectroscopy. TMS is an inert gas, gives single strong resonance of its 12 identical hydrogen, which appears at 0.0 ppm. Measuring the chemical shift. The effect produced by local and internal field are considerably less than the imposed by the external field. The latter produces resonance frequencies at many hundreds MHz, whereas the former produces differences which are only of the order of few kHz. From the chemist's point of view, we are interested in the frequency difference between nuclei in different chemical environments. So it turns out to be convenient to define the frequency scale as a relative scale, that is chemical shift or delta. The chemical shift of any resonance, the unit is ppm, is independent of the strength of the applied magnetic field, despite the fact that the frequency difference in the Hertz between the resonance will alter in direct proportion to the field. This means any kind of chemical shift alignment made one of the spectrometer are equally applicable to the spectra obtained at any field strength. The proton spectra obtained at variety field strength, the chemical shifts of the resonance do not alter with increasing field, although their actual frequency differences do increases. That is, greater peak dispersion is obtained at higher field strength. Resonance at higher frequency are often referred as being deshielded or shifted to low field, whereas those at lower frequencies are described as shielded or shifted to higher field. Now that we have seen the constituent of chemical shift, we shall go to on see what influence this property and how this relates to the chemical structures. Primarily, the intermolecular effect results in substantial changes in the chemical shift. So in most cases, the difference in shifts that are observed can be related to the structural features within a single molecule. These figures displays the shift region, which is various proton resonance. As mentioned previously, chemical shift values are distinctive for chemical environments for a particular nucleus. Thus, similar chemical environments give rise to the signals with similar chemical shift. These are often tabulated to allow us to use chemical shift as a starting point of our interpretation of NMR spectra. Thus, HCO have higher chemical shift than HCN, which have higher chemical shift than HCC. Proton chemical shift are thus a measure of electron density, and the more electronegative group attached to the carbon bearing the proton, higher the chemical shift of the proton is. Now we will be discussing about various effects on the proton spectra. The inductive effect is much serious effect on the chemical shifting. The degree of shielding about the nucleus will be strongly influenced by the electron density surrounding it, which in turn will be affected by the presence of electronegative and electropositive neighbors. Electron withdrawing groups will tend to draw electron density away from the nucleus, so reducing the shielding effect move the resonance frequency to the higher values. The opposite arguments apply to the electropositive groups. The effect tends to fall rapidly and the nucleus become more distant from the inductive group. For example, in proton spectroscopy, effects may be readily observed over 2 or lesser extent 3 bonds, but are oftenly vanishing small beyond this. The effects of multiple substituents tends to be approximately additive, and tables may be used which allow one to predict the shift of a nucleus in a given environment. The hydrogen bonds are also very much effective in chemical shift, usually involving OH, NH and SH groups, have an electron withdrawing effect on the proton involved, may move such protons to high frequencies by many ppm. They may occur intramolecularly or intermolecularly. The shift of any hydrogen bonded proton tends to be hard to predict with any accuracy, as it is generally represent at population averaged shift between the hydrogen bond state and the non-hydrogen bonded state. Shift due to the intermolecular hydrogen bonds are therefore concentration dependent. For example, carboxylic acids often occur in solution as hydrogen bonded dimer, so that the acidic proton resonate in the 11 to 14 ppm region, but shift to lower frequency as the solution becomes more dilute. Temperature also has a large influence on the shift of the hydrogen bonded proton, which increases the temperature generally causing shift to the lower frequency. And in aromatic systems, electron density may also be influenced by the presence of group which induce mesomeric effects. For example, compare the influence of the plus M effect of the methoxy group with the minus effect of the ester group. We can see clearly these effects can be operative over many bonds in contrast to the shorter range inductive effects. Anisotopy is a typical case in chemical shift effect. The functional group which contain multiple bonds so have electrons which have circulated in a applied magnetic field. In some cases, this circulation of pi electrons happens more readily about one particular axis of the molecule. This produces regions of magnetic anisotropy. For example, in a carbonyl group CHO, this circulation leads to the de-shielding. The proton observed, the peak is 6.9 to 10. Whereas the effect causes shift to the higher and lower frequency would depend not only on position but also the atom in the bonds. The hybridization of the carbon atom also has some source of influence on the shift of the attached proton, as the electronegativity of the carbon increases as it takes one or more S character. The additional influence is found in case of aromatic rings. The proton resonance of benzene, for example, occur at 7.3 ppm, so are considerably less shielded than proton in a lone double bond. This is attributed to a caused by the circulation of pi electrons around the ring on the application of external field. The circulating electrons produce a field that adds the external fields of the position of the protons, so causes shifts to higher energy frequency. The comparison between proton and carbon based spectroscopy is follows. They both are quite similar. Carbon 12 has high abundance is nature, but due to its spin 0 it cannot be detectable by NMR. But the carbon 13 is a natural abundance of 1.1, has a nuclear spin of half, so gives rise to the NMR signals. Since 1.1% of carbon atoms in the molecule are detectable by carbon 13 NMR, the data is more difficult to acquire than corresponding proton data. However, even a few milligram of sample have billions of molecules present, so that there is a very high probability of each carbon atom being carbon 13 in some of the molecules. Problem of sensitivity are largely overcome by using greater number of scans or more concentrated sample. Typically, we can obtain a proton spectrum using 4 to 16 scan or 10 to 20 milligram of sample, whereas the corresponding carbon 13 data will require 200 to 2000 scans to obtain a reasonable spectrum. Thanks for watching.